I don't have that. It's terrible. It was just like this. Of course. Actually. It was nice. It's just like one.
Okay, we will begin. So today we're covering topics that are super important, but also just very universal to all of the field. So, and those top concepts are overfitting, regularization, which is the primary way of dealing with overfitting, model selection, which is really another kind of way of looking at what regularization is doing, and then cross-validation, which is a very practical way of evaluating a model, tuning a model, tuning the regularization terms, and something that you always do with a data set. Okay, so the first, starting off with, it's going to be a bunch of pictures in this slide deck. So we have, and this is, you can think of this as a regression data set. So here the variable that you're trying to predict is on the y-axis, and it is continuous. So it's a continuous target variable, and you're trying to predict it with the variable that's shown on the x-axis. And in the middle and rightmost panels, you have two candidate models. And my question to you is, which of those two models, the middle or the right, is better, and why? Okay, why would you say the right one?
Because if you have a point that's not in the data for the left one, that's not going to work. So with that.
Mm-hmm. That's exactly right. It definitely looks like, because the middle model has done a really good job of capturing the variability in the training data, and so it actually has zero error. So I should probably also point out, so we talked about the loss function last time. I'm going to stay on the slide. I'm just going to write one thing. So the loss function, someone else.
That's me. I just want to see
Okay, cool.
what it looks like.
Yeah, cool. So I guess I'll stop screen sharing for a second while I write this. Pause share, that'll work. Okay. So Andrew, are you on the Zoom?
Yeah.
And can you see me?
Right now, no.
Okay. Okay. Stop share. Okay.
No,
Yeah. I guess when you pause sharing is something where, like, if you have to, what's that?
I think you can move ahead of the slides or whatever.
Yeah, or like if you get a sensitive email that you don't want to be forever read on YouTube. Okay, so hopefully, Robert, you can see what I'm about to write on the board. Loss loss function. So loss function, this is the thing that you're trying to minimize generally. So last class, we saw the logistic loss function when your target variable is either -1 or 1. And what we saw is that the loss was I don't even need to put the W here. I was going to say. So yeah. So basically, the thing, and I put a negative here because we are actually maximizing the log. We are actually maximizing the log likelihood, which is equivalent, which is a concave function. The logarithm is a concave function, and we want to do everything with minimization. So if you want to minimize a function like this, you just take the negative of the log and then you minimize it. That's going to bring so the log of every probability is a negative number, and so this means that, let's see, the log of every probability is a negative number. So when you negate it, it means that you're gonna, you're gonna end up negating it. Means that if you minimize it, you're actually going to be maximizing the probability. But the thing that I'm trying to convey here is that if you're if you have a regression, so maybe a logistic regression, and let's just say a linear regression. Your loss function will be, I think, more intuitive. So you can just take your whatever the thing you're trying to predict, and you can subtract your estimate from it, and you can square it. And so minimizing this, you want to minimize this in a linear regression, and the y hat is just a linear function of your data. So it'll be something like w1 x1 plus w2 x2 plus term. And so what you're going to want to do, so the y hat here is a function of your data, and then if you have many data points, you're going to want to just take the summation. So this is called the mean squared error. And this is the loss function that you should always use for regression problems. So the thing that you're predicting is continuous. This is always the thing that you want to use. I don't know if I've asked you, but this is not a good choice if your target variable is discrete, right? So we could use this loss function for logistic regression, but that would not be a good choice. You can still do it. It's just you won't learn as quickly or as efficiently. And so this is called the negative. This is called, that's mean squared error, and this is called a negative log likelihood. And so the reason I bring this up because when you perform a problem like we see on the board, are there lights not on that should be on this? I feel like things seem different today. Maybe it's just my brain. Back to screen share. Okay. So the reason I bring this up is because the loss value of the middle model is lower than here, right? And so if you're strictly speaking, the middle model has achieved a lower loss, so it's produced a lower error. But as Andrew said, the reason it's probably not a good model is because when you get a new data point, it will not fit this polynomial here will not fit that new data point well, most likely, unless, of course, unless there's actually some pattern in the fluctuations along this axis, right? From what we can tell right now, there's just that linear trend in the data. So the model on the right is better, and we know intuitively why it's better, but I encourage you to try to think about mathematically or statistically how can we quantify that the model on the right is better than the model on the left. So one way of thinking about it, I think I've said before that, you have your model is going to be, let's say it's a polynomial. It's some polynomial function of x, and x is a vector here. So or actually, let's take the case where you have a single feature for the sake of this argument. You can construct an arbitrarily complex function just by adding extra terms in the polynomial. And Robert, I'm sorry you're not seeing this, but you'll see it next time I go up on the next time I switch, and it's not critical. So that's a polynomial of degree d, and the thing is that model family can capture both of these models. And so the way to quantify why the model on the right is better than the model on the left is that you want to pick a model that achieves a low loss function on the training set, but is simple, so has fewer parameters. And so the number of parameters in this model is huge compared to that model, right? The model on the right basically has two parameters, a slope and a y-intercept. Now, this model here has, can anyone guess how many parameters the model in the middle has?
0.
Yeah, exactly. It's a number of points in a data set, basically. Probably +1 because the intercept. But yeah, it's exactly. So you can always fit, if you want to fit, a set of points, you just need to have as many coefficients as you have samples. Okay, and so that concept is I showed it in the previous slide for regression, but it holds just as well for classification. So here's a really, I think, easy to grasp picture where you have two classes, a blue and a red class, and we have two decision boundaries. So decision boundary means, where is the threshold for what you call a positive example and negative example. And so again, here we see that the green boundary, so the green boundary does a better job of classifying this data, right? So it has zero error. Every marker, this is training data. Every marker here is on the right side of the boundary. However, again, the black boundary is probably a better choice because it seemed, just from looking at this, it looks like these are just, the fact that this red point is here is probably just some measurement noise, or that's an outlier. And so the goal is to, overfitting happens when you unknowingly capture the noise, essentially. Overfitting is finding structure in the noise. And the thing is, in 2 dimensions, you can see it. Even in 3 dimensions, you can see it. But you're not going to see it in 1,000 dimensions. And that's the problem, is that, you at a certain point, and you're certainly not going to see it in millions of dimensions, which is what many common day data sets do. And so we need to have one way of knowing when it happens, and B, having a way to prevent it from killing our model's performance. And so, right. So basically, what I said is already on this. What is on the side is what I've already said. Is that you can always construct a complex decision boundary that separates the classes. However, it's unlikely that that complex decision boundary is going to do a good job on new data. And so keep in mind that your training data, so you have your data comes from, there's some, you can call it God or a genie that produces your data XY, right? And your training data is just a very small sample of that distribution. Right? So when you collect some data, you're essentially sampling that joint distribution between X and Y n times. And so especially if X is high dimensional, your samples are very sparse. I mean, I think I showed you that we had a slide earlier that was the curse of dimensionality, where, to tile a space in 1D is easy, to tile a space in 2D is easy, but once the number of dimensions grows, tiling the space is really hard. And that's what every sample is essentially a tile in the space. And so the key is you want to capture the structure in the data, and then the structure in the data is what is present in that probability function. Because the other thing is, I'll write this, but essentially you get one sample of the data at training, and you get another sample of testing, and those samples will, in the real world, they'll always look different. Okay, so this is Occam, I think. I can't remember now. I made this slide years ago. But the Occam's razor principle is still super relevant. And the definition, I mean, there are many definitions of it. And there's a quotation missing in the bullet. But the basic idea is that a simpler model should always be favored unless you have compelling evidence to reject a simpler model for something more complex. So you should always select a solution that makes the fewest assumptions about your data. You don't want to say. And so in the case of the polynomial, the simplicity of that model is the number of coefficients in the polynomial. So it's the value of that lowercase d. And so again, unless you have very strong evidence that you need more coefficients, you should always aim to minimize the complexity of your model, because that will give you better performance on new data, which is all you care about. You don't care about your training data. You can always get great, get low loss or high accuracy in your training data. The only thing you care about is how you're going to do when you get new batches of data that you have to actually make predictions on.
And the hierarchy between minimizing loss and keeping it simple and reducing your complexity is in our form of a balance, whatever is best for you. Like I said, keep it to a single term, but
Yeah, it's well, the nice thing is, and I'll say this again. No, there is. I mean, there are people have I'm gonna switch to the board. Hold on. Too many windows. What is this? No, I don't want to share right now. Okay, so this is where cross-validation is really, this is where having a lot of data, by the way. Remember I said the answer to all problems in machine learning is get more data. And this is very much the case here. So what you're gonna do when you actually when you are architecting, developing a model, well, you remember I said that you will spend, you will acquire some data. This will be your X, features X. And this is your label Y. This is the thing you're trying to predict. And so, the easiest way to quantify that trade-off is, you have a bunch of examples, and then you will learn your model. And I gotta make sure I leave enough time. I have a Python demo that I posted right before I got here that will actually show you how to do this. You'll learn your model on a section of the data, and then you will evaluate model on this section of the data. And so essentially, as long as you've ensured that that the fitting function has not seen this data, you can always take the accuracy from here as your figure of merit, I believe it's called, accuracy. And actually, I'd say accuracy is not a good metric in classification generally, unless your data is exactly 50-50 split between the two classes. So this is this is area under, I'm not gonna write out the raw curve. And this is, I'm just gonna say this, area under, I haven't taught you guys precision recall yet, but I will. It's very important. Area under precision recall curve, which is just another, it's a much better metric of classifier goodness compared to accuracy. So I skipped over the basic decision theory lecture. I am going to get back to it. It's simple, but I wanted to get to the actual modeling, learning algorithms quicker in the course. So, but the example that in one of the slides that I didn't cover is if you have a model where if you're predicting benign and malignant, and the prevalence, actually I'll write it in the terms. So it's called the prior. If you have a prior on that a given tumor is malignant is 0.99. In other words, there's a 1% prevalence of malignancy. right? So what is wrong then with using accuracy to measure, you know, the goodness, let's say goodness, quality of some classifier on that problem? Why should we not, if the problem is to classify, if the Y here is benign or malignant, and the malignancy has a 1% prevalence, what's wrong with using accuracy? Or is there anything wrong with using accuracy?
Depends how you use it.
No, I don't think so. I think it's always bad. I think it's always a bad idea when you have. So the problem is if I call everything benign, I get a 99% accuracy, but I haven't learned anything. I haven't even looked at the data, right? So, and this, by the way, this is a 99% prevalence is not that uncommon in medical data sets. It's not. I mean, there are things you do, by the way. Sorry, my handwriting is really poor, always, but especially today. So if you have, so the problem with, you know, if you have a data set that has, you have, let's say, 990 examples of, you know, you have 990 examples of a benign tumor, and you have just 10 from the malignant class. Again, accuracy is not a good measure because there's no way of like you have to look at what you're really interested in, first of all, is capturing those 10 malignant examples. Those are really important to you. That's one thing. So by the way, what is done in that problem a lot is you will artificially modify your data set. So what you're going to do, so this is done all the time. Basically, you take these examples and you just repeat them as many times as you need, so that the prevalence matches. And then it's kind of a weird thing because you know, your model is just seeing the same example over and over. However, the reason that it actually works is because, remember our loss function? Our loss function is you know, it's for logistic regression, it's the sum over the data. And so the problem is that if you don't do this balancing, this summation has 990 terms from one class and only 10 from the other class. And so this loss function will end up not caring at all about this. And it will just converge. What's going to happen is you're going to converge to a classifier. And I guess I can draw a picture. Over here. So if you have, it's called imbalanced data sets or skewed data sets. So if you have, you know, I'm not going to draw that many of these, but you can imagine. Let's say there's some noise here, like this. What it's going to do is it's gonna completely disregard these examples, and it's gonna draw the decision boundary. It's just gonna say, I'm gonna put my classifier here, and I'm gonna call, and everything above here is nice and warm over here. Everything above here is benign, and then I have my accuracy will be great. You know, my accuracy will be 13 out of 16. So if you know, if I were to draw more of an circle, accuracy would be great. So accuracy is not a good measure. But to answer your question, it's not really an art form. This is actually kind of, we actually know what we want. We want good performance on unseen data. So we can basically learn a bunch of different models and evaluate each of them on new data. And what probably the simplest thing to do is just to go with the one that gives us the best performance metrics. Now, in practice, what ends up happening is that when you have a really important problem, such as cancer diagnosis, you are really going to take the time to exhaustively span a large number of models. And what ends up happening is that if your test data is not, if it's not a huge sample, sometimes you'll get lucky, and you'll just the model that got you good test accuracy or test good area under the curve on the test set got so because if you evaluate 1,000 models, just sometimes you just get lucky. And so you have to be careful with how many models you actually sweep through. But in theory, we know what to do. We know that we need to get good performance on new data. Okay, so regularization is a way that we, shield ourselves from overfitting. And so essentially what we're saying is that we want our weights to be small, or we want our weights to be sparse. And so, if you have, I need a smart board. So if you have a model where, let's say you just have a regression model where and so the model parameters that you have to play with, you can essentially you can measure how big they are. So how big they are is essentially just the this sum of square rooted, or you can measure their what's called the L1 norm, which is the sum of their absolute values. And the key thing here to note is that, this is probably not the most intuitive thing, but when overfitting happens, the W's tend to grow really large in magnitude, and sometimes a lot of them will end up having large values. So the magnitude of the weights is a way to diagnose overfitting, and consequently limiting weight growth is one way of preventing overfitting. So if you're not letting your model capture those crazy variations in the training set. Okay, so I've already talked about this, but the loss, this is a really, the quadratic loss or the mean squared error loss is it's the simplest loss function to understand. And so when you're performing your fitting function, your fitting procedure, your training, you're looking to find the W that minimizes that. So you want your model prediction y hat to be as close as possible to y. Okay, so y hat is where your model comes in. So the reason that W doesn't appear anywhere on the right hand side is just because it's implicit in the y hat, and so is the x. The x is there as well. The data is there as well. And so we want to use that loss function. We want to use that loss function, and we want to augment it to add this regularization term. So I touched upon the notion of a penalty term last class, and what I described is so this lambda, right? So what you're saying is that the R, the subscript R there stands for regularized loss. So what you're doing is now, instead of just minimizing the loss, because remember, we're going to be minimizing L of W or LR of W. And so by adding this penalty term, you're now telling your model, yes, minimize the loss, so get as many of the data set points accurate, but also penalize really large W's. And so what it's the two terms here on the right hand side, the LW and the penalty term, they're competing, right? So you larger W's will make this value decrease, but larger W's will make this term increase. And so that penalty term has made it more difficult to for you to end up selecting a complex model. And the art here is that now we have a new parameter, which is the lambda. And the lambda is called the hyperparameter, something that if you've done any reading on machine learning on your own time, you've encountered this term. So it's called a hyperparameter because W is your parameter, W is your model. Lambda is a different type of parameter. It's not actually in your model. It's a parameter of your model fitting procedure. That's why it's called a hyperparameter, because we distinguish it from the actual model coefficients. And this is a typo. This says we must somehow choose the value of W. It should say lambda. So the problem is, how do we choose lambda? So if we make lambda very large, what's going to happen to our model? What's going to happen if we make lambda very large? What will our model look like? What will our W look like? Yeah, exactly. Are probably too small. You're going to end up with too simple of a model. What's that? Potentially on the training set, yeah. But it could also, but sometimes if you have very noisy data, you'll actually get better performance on the test set. And so if lambda is 0, there's no regularization, and W will be whatever it needs to be to minimize the training set loss. And so, you know, if lambda is 0, then your W is just going to focus on getting these training labels correct. So I should label this is called the training set here. And this is called the test set. And nowadays there's now a third type of set called it used to be called the holdout set, and I still call it, but now people like the term validation set. So the validation set is actually was used for tuning lambda. So now you almost have you have almost two you think of it as a second training set. You have one training set like this. What I'm talking about is like the deep network world, the deep learning world. You'll have one. So you'll have 3 partitions here, 3 sets. One set to tune your lambda, another to tune your W, another set to tune your lambda, and then finally a test set where you actually make predictions. So all you care about is this, right? The test set is your simulation of what's going to happen when you actually go and make predictions and use it in the world. So the bad news is that the value in practice, selecting the value of lambda is super important, which sucks, because if we don't select it right, our model will not achieve good performance. And so tuning this hyperparameter is like a big part of what the data scientists at Google do, I think. I'll have to cut that out of the video, but essentially hyperparameter tuning is kind of occupies a very large amount of the work in model fitting. There's also the architecture, so like selecting what kind of a model. So, you know, are you going to do a logistic regression or a 10-layer neural network? But once you've made that choice, regularization is like the key thing. All right, so L1 regularization is very similar. It looks almost identical, except that now you're not that this is this is the notation for the L1 norm. So in other words, is the sum of absolute values. So I have a picture on the next slide that I think does a good job of showing you the difference between these two. I had when I first saw this, I'm like, how does this possibly lead to a lot of zero weights? But it actually does. I've let just experience convince me that this really does work. In the sense that if I minimize this function, LRW, a lot of the WIs, a lot of my model coefficients will end up being essentially zero, which is a nice thing because it's very, especially in our world in biomedical, where so in many machine learning problems, all you care about is good test of performance. And as long as the model works, you're good. You don't care what the W's are. In our world, though, we really want to interpret the model, right? So if we're diagnosing cancer and we're using some algorithm, we do not feel great about not understanding what the algorithm is doing to make those decisions. And this is a huge debate right now in deep learning because what happens, well, we already maybe do have an AI robot that has a higher success rate in performing surgeries than a surgeon. And so the error rate of the robot is lower, but people still don't feel comfortable going under the knife with a robot doing the surgery compared to a human. And this is a huge debate right now. And part of the problem is that we don't really know what that robot is using to guide the information as to what to cut or whatever. I don't know anything about robotic surgery, but that's kind of the essence of the problem is we know what the human, if you ask the human, what are you doing to determine where, what angle you're cutting at, where you draw the boundary for the resection. You can ask the human will be able to tell you. The radiologist will be able to tell you, I'm looking for this pattern, see that, I was just at the dentist yesterday and he was telling me, if your nerve was infected, you would see this hollowness around it. And so the human can tell you what its model is picking up on. We don't yet have good techniques for asking an algorithm to tell us. But in the case of something simple like logistic regression, we just look at the weights. And the weights tell us, which features are important. We can at least know which features are important, which features are less important, which features are kind of capturing redundant dimensions, etc. And so this is great for that because if you have very, very many weights, a lot of them go to zero. And then that the corresponding features are not important. So this L1 penalty, and this is these are the contours of that function. So the contours of the L2 function are spherical, they're hyperspherical, I guess, in the dimensions. So, right, let me unpack this picture. The blue contours are your training set loss. So you can think of it as the accuracy in your training set. And so if we were just gonna go with the model that gets as many examples right on the data set, we will pick this model. So W1 would be this value and W2 would be this value. Oh, did I switch out? Oh no, I'm still on the slide. Right, so with L2 regularization, you're going to want to pick the solution that is closest to the origin, right? Because these are the contours of the Euclidean norm. So these are the contours of that L2 penalty. In other words, the magnitude, every vector here has every vector around this circle has the same norm. And so geometrically, if you are constraining your model to have this Euclidean norm, this L2 norm, the solution is going to pick is this one. And, you're going to, I don't know if this is drawn to scale, but basically you're going to pick the point that is, if you draw a line from here to the origin, from the unregularized solution to the origin, it's going to pass through your W star. So the coefficients of the regularized model will be here. So essentially you're saying, I know that this model doesn't get as good performance on the training set, but I believe that this model is just overfitting, and I'm going to go with this model.
And tuning lambdas, making that circle bigger or smaller.
Exactly. So the bigger the lambda, the smaller that circle. Yeah, tuning the lambdas, and there's actually a strict equivalence. For every lambda, there's a corresponding radius that circle corresponds. For every lambda has a corresponding radius where basically you're selecting your W's from there. And this is the L1, this is that absolute value norm. This is the sum of absolute values. And you see here that how do I convince you of that it would choose? So if you're trading off these two, so if you have to pick something that is not outside of this rectangle, but minimizes these contours, it would in fact pick this, right? Because these the function is getting bigger this way, right? And the problem is that the circle extended here, and so it would have captured the contour of somewhere over here. But because of the diamond, I'm just going to call the diamondness of this contour, you end up picking something where the W1 coefficient is 0, right? So the key thing about the picture on the right is that one of the coefficients has been forced to 0. And so your entire model is ignoring the first dimension of your the first feature. And all it's doing is using W2. And in high dimensions, what you're going to see is that, especially with higher values of that lambda, many of the coefficients will be selected to 0, which is really nice. It's essentially a way of performing what's called feature selection. And so you have many features. You do your biopsy, and you ask your text to just give you every measurement you can think of. And as long as you regularize your model with something like L1 aggressively enough, you're not going to overfit. And this is still super, like, even no matter how complicated the model architectures get, L1 regularization is used basically by everyone. This is a great thing, because you're doing features, because the model is doing feature selection for you. You don't have to worry about not including uninformative features. Of course, the trade-off is that you do have to find the right value of lambda, which is where the work is.
And the error is the same in the training set, right?
Yeah, exactly. The error is on the error, exactly. So the error is exactly whatever. This is the smallest error, so this is minimum error, and then the further everything on this contour has the same error.
And it's always a perfect sphere. What are you saying? At the sphere, the contour.
The only for the quadratic, yes. For the quadratic loss, it is, but not for the. But even for the logistic regression, the negative likelihood, I think, is also a convex. So for convex functions, this is what the contours look like. So we also haven't covered gradient descent, but for convex functions like the quadratic, there is really just one minimum, and the points around them and the contours around that minimum look like this. Sometimes it won't. Sometimes they'll be ellipsoids, I should say. They're not always perfectly. They're not symmetric, but they're ellipsoids. And so, yeah, that's actually a good observation, is that these two models both achieve the same training loss, right? Because the selected model, anything along this contour, by the way, is going to have the same model loss, the same training loss, but they will generally differ on how they do on the test data.
The weights are.
What's that?
The weights are.
Yeah, the weights, exactly. The weights are different. Yeah. And very different, right? So in this, you're using both features. You're using X1 and X2. But in the model on the right, you're only using one feature. Yeah.
Will the norms ever come closer to having like no error? Like intersecting with the contours or no?
Well, they are intercepting with the contour. So sometimes, yeah, if you make your lambda very small, then if this contour was out here, then you would pick that. Like that's the minimum. So you can't get any lower than that. That's what this picture is saying. So yeah, if you make your lambda too small, then the contour will cover the minimum point, and then yeah. Okay. So I've already said this, training and test set. So basically you never, ever, even in linear regression, evaluate and you never learn and evaluate your model in the same data set. And the biggest reason for that is the problem with the training error performance or training loss is that the bigger the model, the lower the loss. That's guaranteed. So you can try this out. Just add, if you have a regression problem, you just add random noise to it and fit a model. Your training loss will always adding more parameters will always decrease your training loss. So it'll always make your performance better. And so that's a very good indicator of why training loss is not a good metric for your model. And so what this slide is saying is that you always need to partition your training sets, your data set, into a training and a test set. Your training set is used to learn your W, and the test set is learned to evaluate your W. That's clear. All right, cross validation, super important and super easy. This is one of those things I think I told you, Professor Parra taught me machine learning in one sitting, and this is one of the things I think that was in that session, is how to do cross validation. So you don't just, in the picture on the board where I have the top 30s for training and the bottom 30s for testing, well, that's all fine and well, but why would I just not? I'm not making the most out of my data set. I'm not using the bottom third to inform my model. And cross validation solves that problem. The idea is that you split up your data into what are called folds. So it's like folding a page into 3 or 5 or 10 sections. And I've given you the pseudocode here. So there's, let's say, a fixed number of iterations. So if you have 5 folds, you'll have 5 iterations. So you have a random assignment between what goes in the training, what goes in the testing. And then you will learn your model on the training set and then evaluate your model on the test set. And then you store the result. And then you go to the next iteration. And again, now you have a different partition of the training and test set. So like for example, if you have 10 examples, maybe on the first iteration, examples 1 to 8 will be your training set. Examples 9 and 10 will be your test set. On the next iteration, it will be, 1 to 6 and 9 and 10 will be your training, and 7 and 8 will be your test. And then you basically, there are many ways of partitioning a data. And the way you partition the data is determines the type of cross-validation. But there are really two types that I show you in this lecture. One is called K-fold. So here's a picture of what K-fold looks like for 5 folds. So when I run this, I always make the test set, I start with a test set at the end, and then I kind of incrementally. So on the first cross-validation iteration, let's say the last 20% will be my test set, and then I just move it up in each iteration. Of course, my MATLAB and Python they have functions to basically just, if you have 100 examples, they'll give you the indices to partition at every iteration. So you don't actually have to code the random number generation. So I think this is a very straightforward. You're training on a distinct subset at each iteration. The thing about this is that this is a stochastic thing. So if you run this and your friend runs it, unless you're using the same random number generator, you're going to get different results. And this has some, and even if you run it twice, you're going to get different results, which is a problem because now, and oftentimes your findings will be different depending on just the random number generation seed. And that's then what do you interpret from that? That's one thing. The second thing is that the proportion of training to test, right? So if you have 5 folds, then 80% of your data at every iteration is being used for training, right? If you have 3 folds, 2/3 are being used for training. So, but that right there, there's a fundamental difference. So if you have 100 examples and you do 5-fold cross-validation, you are asking your model, you're asking your learning algorithm rather, to find a model from 80 samples. If you're doing 3-fold, you're asking your learning algorithm to find the correct model with 66 samples, right? So this is not a trivial parameter. And so, by the way, let me ask, this is a question I like that. I usually ask students in my lab this, but let's say that I'm choosing between 3, 5, and 10. Which one of those do you think is going to give me, in general, which one of them is going to give me the best test set performance? 3, 5, or 10 folds? Any ideas? It's not an easy question.
10.
Yeah, why do you think 10?
Because you have so much training data.
Yes, exactly. Right. So 2-fold is the hardest. 2-fold is 50-50. You're asking your model to learn. You're asking your algorithm to learn the model with only half the data samples. So that's a harder problem. Like just from like a statistics standpoint of like you have to get to the bottom of the hill, but you only have half the data for your loss function only has say 50 samples in it. So the more folds you have, generally, the better your test performance will be. By the way, one thing that you should consider is what's going to be my training set size like in practice, right? And if your training set size in practice is going to be huge, then I would advocate for what's called leave one out. So leave one out. This is the last slide for the day. Leave one out is a special case of K-fold where the number of folds is equal to the number of examples. So essentially, if you have 100 examples in your data set, then you will take, for the first iteration, you'll take the first 99 and test on the last, and just test on one sample. And that's fine, right? It's okay that you only have one sample in your test set, because you store that result. And then when you go to the next iteration, you have another sample. So you have many independent samples of performance. So the nice thing about this is that this is no longer stochastic. So everyone will get the same value for the average test set performance here, right? Because there's only one way of doing this this procedure. You're always going to use, everyone's going to use the same 99 for training throughout.
But that would be only if the two people chose that 100, like 99, the first ones, and then the index value only the last one. Then
But you do it 100 times.
But then the point is that every so they're not going to do it in the same order, right?
That's what I'm saying. Does the order matter?
No, it doesn't, because you're essentially, you're looking at, is the 100th in this picture, is the 100th example correct? Yes or no? Let's say it is. And then you go up to the 99th. Is that one correct? Yes, it is. And then every example has been in the test set once, and so you're always averaging over the same 100 numbers.
But then you can do, I mean, for one, you cannot do statistics because like for
Okay.
what?
You have 100. You have 100. You have 100.
For your W's are different.
Your what?
Your W's are different for each.
Yes, your W's are different. Yeah,
So
your model is different, but that's okay. Your W is going to be different. So when you actually, by the way, let's say that this is all you had. And so here's a question for you guys. You have 100 examples. And like you just said, every time you do a training, you get a different coefficient. So what do you put out there in the real world? Like, how do you train your model to put out, like which W do you go with in practice? You have to go with only one, right? Well, there's ensembles, but you have to go with one. So what would you do? No, don't know. Never do that.
Of course not.
Never not.
You can.
You
just-
throw in all the data usually. In this case, if you only have 100.
Oh, you do it. I see.
You do it again. Now, you would still, that's probably the most common solution, but what you can do, what people will do, another alternative is that if you do 5 of these, you'll go with the one that give you you'll just pick the one that give you the best training test loss. Or what you do is you do this procedure not for model selection, but for the lambda selection. And that's more sophisticated, but basically you do this cross validation not to learn your W, but to learn your lambda. And then you take that lambda and you run a final model fitting at the very end on all the data. If that makes sense. So like I would say if you only have 100 examples, that's a pretty small value, I would say throw it all in there and go with that W. But of course you're going to need to have some lambda regularizing that model, and probably to tune that lambda you would do a cross validation procedure. We'll see examples of all of this later in the course. Oh yeah, this is time consuming, right? You can't do this if your data set's a billion samples. So that's kind of the one drawback of it. And sometimes it can give you overly optimistic results. I've seen this happen where the leave one out, there's something about the leave one out that sometimes it gives you, like I've worked on projects where the performance in practice, and I think it's because, keep in mind that this is data that, like, if your data has any sort of like dynamic component, like a time component to it, So a classic example is if you're predicting stock market prices, what people will do is they'll collect data from the past and they'll fit some model to predict stock prices. Works great. However, there's something called look-ahead bias, where now in your model fitting, you've inadvertently used information from the future to make predictions for the future, or to make predictions of the past sometimes. And so in the real world, you can't do that. You only have access to what's happened at this point. So that's like a classic problem in machine learning. Whenever you're predicting something that has a time domain component to it, right? You'll collect some retrospective data, but if you're not careful in how you do your training and testing, basically, whenever you're working with time series data, you always have to make sure that your training set came before your test set. And the real bummer is that that never works as well for things like stock market returns, but also things like epilepsy prediction, seizure prediction, things like that. We'll do the example that I had ready on Monday, and hopefully you guys will appreciate all this more.